Okay, for this series of videos, we're going to be looking at confidence intervals and how to properly construct one and show the appropriate work, etc. So, one thing you always have available to you is the reference guide for the AP exam, whether it's for tests or for the exam itself. It won't give you the assumptions and conditions, but it will give you a way to come up with the appropriate formulas. All right, so if you look carefully at this page of the document, you see that it's exactly the same as it was for hypothesis testing. So there should be some familiarity there, right? But for any take-home assessment, you'd have access to this. But if you were to do something in a classroom setting, you would be expected to know this information. So the first one that we're going to look at is the one population mean sigma known. Packaging device is set to fill detergent packets with a mean of 150 grams. The standard deviation is known to be 5 grams. It is important to check the machine periodically because if it's overfilling, it increases the cost of the materials, whereas if it's underfilling, the firm is liable to prosecution. All right? So the false advertisement. A random sample of 25 filled boxes is weighed and shows a mean net weight of 152.5 grams. Can we conclude that the machine is no longer producing the 150 gram quantities? We're going to use a confidence interval to basically support our work. All right, so let's investigate. First thing I'm going to do is restate the question. Is the population mean still 150 grams? All right, so that's our status quo. All right. We need to know what the sigma value is in order to use a particular approach known as the z-test. But you wouldn't have that defined for you going into the problem. You're not going to have a title to each question, so you'll have to kind of use that to sort of flesh out what the appropriate test is. So the type of interval. And just like we did with the hypothesis test, you're kind of better off thinking about reasons first. So we're testing about a mean. Where sigma is known. Known. All right, so that makes it a z-test. If we did not know what sigma was, then different story. All right, assumptions, conditions. I'll take it as a typo. I had it labeled differently on the other one, where it was assumptions in one section and conditions in the other. I like that a little bit better. So the first one to submit that to me gets the typo bonus. And be on the lookout for Easter eggs. I'll make little references in these videos, and if you catch the Easter egg, then that's worth some bonus credit for you. There is a maximum of 3 points, 3 bonus points for typos, but there is no limit to the number of bonus points you can get for an Easter egg. Right? So assumptions, conditions. So for that, you can reflect back to the first page, but simple random sample, normal distribution, and n is greater than 30. And then in this case, we need to know that sigma, we need to know what sigma is. All right? So reading. A random sample, so we could assume a simple random sample. And we have 25 filled boxes. All right. I'm looking for the words normal distribution. Standard deviation, periodically, cost of materials, etc., etc. I'm not seeing the word standard deviation, normal distribution. So we have conditions. Sigma is known. We have a simple random sample. We have an assumption. Normal distribution. And, you know, I'll just write a little explanation here. Not stated. N is not greater than 30. All right, so my calculator function is going to be z interval 1. No, it's just the interval. I was thinking of the props. And this is one of the pitfalls of not having a class in front of me. I got to go back to this. It wasn't this type of interval. It's the interval. All right. So the calculator function happens to match precisely with the name of the I almost said hypothesis test again, confidence interval. So we're in good shape there. Now the formula for test, formula for confidence interval computation. So x bar, that's our point estimate, plus or minus, here we have z alpha over 2 times sigma over the square root of n. All right, so this is our point estimate. Little refresher there. And this is the margin of error. All right, I won't go through that for every particular case, or every case, particular unnecessary there. But I will go through it this one time just as a refresher. It's been a while. All right, so we want to see if 150 is going to be reasonably contained within our confidence interval. So we have 152.5 and 5 along with 25 for our n value. All right, so I'm going to jot those values off on the side here just so I don't have to continue going back and forth. All right, these are relatively clean numbers, so that's your key indicator that this is fictitious data. All right, so you know, not that that's necessarily going to be, you know, required knowledge, but you can kind of foresee a situation, you know, a multiple choice question, or even a free response question where they say, "How do you know that this data set is fictitious?" You know. You never know what these AP College Board people are thinking. All right, confidence level, I believe, was 95%. So that makes alpha 0.05, which makes alpha over 2 0.025. Now we need z sub alpha over 2. All right, so that's, we've done this enough. I'm just going to allude to what I'm typing into the calculator rather than showing it. So it's going to be in our distribution menu, inverse norm of 0.025. All right, so we're looking at, because we need the plus or minus associated with it, we'll just take the absolute value of this number, 1.96 approximately. Got locked out of editing. All right, so that's what we're looking at there, and this is inverse norm of oh, I'm on the wrong setting for the pen, 0.025. Mean of 0, standard deviation of 1. Those should all be standard settings in your calculator. All right, so, you know, nothing, like I said before, nothing we haven't done before. So 152.5 plus or minus 1.96 approximately times the sigma over the square root of n, like just astonishing how that worked out. So it amounts to 152.5 plus or minus 1.96. I can go with the more exact value, which I have stored in my calculator. Which is always the better way to go. Right? Especially because you're going to have to check this with calculator functions sooner rather than later anyway, so why not have the more accurate response? Right, so we're looking at 150.54 mu, sorry, less than or equal to 154.46 is what it would round to. All right, so just going to do a quick double check on my calculator. Z interval function, option 7, stat test 7. Everything's pretty obvious what you're putting in there. And it rounded to those values, so we're in good shape. Now it's conclusion time. Conclusions for confidence intervals are much easier, but we do have to answer the question that's being asked. Can we conclude that the machine is no longer producing the 150 gram quantities? All right, so we are 95% confident that the population weight will lie between 150.54 and 154.46 grams. All right, so the null hypothesis of the equivalent hypothesis test would be that mu, I'll just jot it down here, always equals, so mu equals 150. All right, so this measure would be inconsistent with that claim. All right, so let me create a little number line here. Nothing too fancy, so I'll just say 150, 160. Let me pop in a 155 here. All right, 150.54, I'm going to zoom in. Extreme close-up, whoa! Movie reference for 1 bonus point. All right. You got to tell me the name of the movie, though. All right, last time I did that one, I had a bunch of people say, yeah, it's a movie reference. I'm like, yeah, I know that. That's why I said it. All right, what is the movie? All right, so this is our 95% confidence interval. Hopefully it's, pretty clear that the 150 is not going to fall within that interval. All right, so with 95% confidence, 150 is not an appropriate value. All right, so can we conclude that the machine is no longer producing the 150 gram quantities? Yeah, yes. Machine not producing 150 gram quantities. All right, so if you compare this to the appropriate hypothesis test, that would cause us to reject the null and go with the alternative hypothesis. All right, telling us that there's something going on here. Whether it's above or below, it didn't really make a difference. It's just the question of whether or not 150 was in that interval, and it's not. So we can't say that it's producing 150. And based on the framework of the problem, there's pros and cons either way. The next hypothesis test is one population mean sigma unknown. All right, so the personnel department of a company developed an aptitude test for screening potential employees. The person who devised the test asserted that the mean mark attained would be 100. Following results were obtained with a random sample of applicants. Construct a 99% confidence interval estimate of the true population mean. This is a nice problem because they didn't ask us to conclude anything other than to create the interval, which comes along with its stock conclusion. But a nice follow-up would be something like, did they achieve the claimed mark of 100? That's beyond the scope of the question, apparently. All right, so confidence interval with confidence level of 99%. That's all the question's asking us for. All right, talking about means, and they told us S, not sigma. All right, so testing a claim about a mean. Even though it's not a hypothesis test, we're still testing. All right. Where sigma is unknown. So this would be a T interval. All right, assumptions, conditions. All right, so if you didn't get the typo bonus for the last video, then maybe you get it for this one. Again, I'd like it to be split between assumptions and conditions, not just assumptions. So separate typo. Well, before I zoom in, we need basically the same stuff as a Z interval, except we don't know what sigma is. All right, so with a random sample, so we got our simple random sample, right? We don't know what S is. So that's, we don't know what sigma is. We know what S is. That's a condition. And as far as the normality condition, I don't see anything there that would suggest that we know anything about normality, so that becomes an assumption. So our conditions simple random sample, sigma unknown, assumption, normal distribution, and again, it's the same justification as the previous video, so I'm not going to write it again. Calculator function, T interval. Formula, very similar to the last one. X bar plus or minus T alpha over 2 instead of Z times S over the square root of N, not sigma over the square root of. All right, this one's at the 99% confidence level, so we'll have to make some adjustments there, but we do need to know some other information. So I know my X bar, 96, S is 5.2, and N is 13. I'm going to just double check that. Yep. We also know that the confidence level is 99%, which makes alpha equal to 0.01, which makes alpha over 2 equal to 0.005. All right, I'm going to use the inverse T function. So second vars on my calculator is option 4. Area 0.005. Degrees of freedom would be 12. Degrees of freedom is n minus 1. And n is 13. So we have that information. So 0.005 and 12. And we're looking at about 3.0545. So X bar 96 plus or minus about 3.0545 times S, which is 5.2, over the square root of 13. Now, in the last video, I showed the separate calculations, or at least in my mind I did. I did it on my calculator. I don't know if it ended up on paper, but in this step, once you've shown all these values, you really can just jump right to the t-interval function and put your information in. The only pitfall to something like that would be if you did something wrong here, you really wouldn't have any way to verify it. So my recommendation has been and will continue to be, try it by hand first, then do it on the calculator and make sure that they jive with one another. So I'm looking at 91.595. The other approach would be do it this way to save some time. And then if you have some time left over at the end of an assessment, then go back and check it by doing it by hand. You know, there's validity to that line of reasoning also. You know, just for fun, I'm going to do it now, though. I find weird things to be fun. All right, so 96 minus, well, I'll do plus A times 5.2 over the root of 13. Low bound is confirmed. I mean, it's much lengthier decimal, but it does round correctly to that. And honestly, if I've confirmed the low bound, I'm feeling pretty good about the upper bound. All right, so as far as the final answer is concerned, we are 99% confident that the population mean mark is between those two numbers, 91.595 I gotta kind of do it again here because I don't want to scroll back. You know what, it's not 8. Could have scrolled back like 8 times already. 100.41. All right, this measure would be consistent. So I'll just put a little X there. With the null hypothesis of an equivalent hypothesis test, only because they gave us that benchmark of 100 in the problem. And 100 does fall in this interval, all right? Not by a whole heck of a lot, but it's still there. All right, so here's, we'll call this 90. I'll make this 100, and I'll make this 110, just to have a consistently lengthed scale. So about right there to like right about there. And so that would be my 99% confidence interval. And so 100 does fall, I mean, ever so barely, but it does fall within that interval, right? But since they were only asking us for the confidence interval estimate, we wouldn't even need the sentence, this measure is consistent or inconsistent with the null hypothesis of a equivalent hypothesis test. I only put that there just to kind of illustrate the connections between the two ideas. And there it is.